more minutes. Who is the next?
We are streaming live.
Yes, but the next is actually Utkash. Utkash is also not around.
Utkarsh didn't join either.
Yeah, and then today is actually this Pooja Thakur, which we have to somehow replace. I don't know whether she will join or not because she has not sent the poster, right?
No, she didn't.
So in that case, I propose that maybe Shoptoshi, if his internet is okay, then he can do because he is the senior most PhD student from our group who can do if everybody agrees. So Priya, 9:26. Yeah, we can start around 9:30 to 33 because people are
Okay.
joining, I think. Priya has joined. Hello, Priya, can you hear me?
Yeah, yeah.
Yeah, so you will be chairing the first session.
Yeah, yeah, sure.
Okay, so you know the rules because you just
Yeah,
have to introduce, you got the affiliations of each of the speaker, and
Right.
there's a chat box where the people will write, and you have to read that chat box.
yeah, sure.
We start maybe because people are still joining, so just wait 2-3 minutes more. So we start at 9:33.
Okay, sure.
Chandan, the recording is not happening.
Yes, sir. We'll just start now.
Okay.
Okay, should we start?
Yeah, just wait 1 minute more. Yeah.
Okay. Okay.
Yeah, I will start with, I will introduce you and then you can start.
Yeah, sure.
Hello, everybody can hear me, right?
Yeah.
Yeah,
And
yeah.
my screen it's
Yeah,
getting shared.
visible, but it's not yet full screen.
Okay, yeah, I haven't done that.
View.
It's fine, right?
Yeah, absolutely. Okay, baby, we start. Good morning, everyone, and welcome to the third day of YouQ-2020. And now I give mic to Priya Batra. She will chair the session. She is from ISER Pune. So, Priya.
Yeah, thank you. So, yeah, I welcome all of you to the third day of Young Quantum 2020. And I'm hoping that you are having a good time in this virtual conference. So, let's start with the first talk of the day. It's by Som Kanjilal. He's from Bose Institute. And the title of the talk is A Contextual Lesson from Froschiger-Renner Thought Experiment. So, as you know, the rules, you will get 25 minutes for the talk and rest 5 minutes for your discussion. So, I give mic to the Som now.
Good morning, everybody. So, first of all, I would like to convey my gratitude to the organizers of this conference because the work that I am giving a talk on is still unfinished, and I was not so sure that whether or not the organizers will allow me to present it, but still they did, and I'm thankful for that. So without further ado, I'll just start. So the main idea of this talk is to understand what the Frauchier-Renner thought experiment says about the quantum contextuality. I'll start with a little bit of motivation on why contextuality is relevant for this talk, and then I will discuss Frauchier-Renner experiment and what does contextuality tells about it. So before start, I'll just give a little bit basics on the propositional calculus. So this propositional calculus mainly deals with propositions which can take only truth values, true and false. So I'll take basically, if the proposition is true, I'll take it as 1, and it is false, it is 0. So for two such propositions, alpha and beta, these propositions are the basic unary propositions which takes only one argument. That argument can be true and false, true or false. And with those unary arguments, we can consider binary propositions such as if alpha is true, then beta is true, which is nothing but alpha implies beta, that I have denoted it as alpha double arrow beta. And then we have the conditional truth table that is defined as this. If alpha is true and beta is true, then alpha implies beta is true. And you can see that if alpha is true and beta is false, then the alpha implies beta is false. So condition, if our premise is such that alpha implies beta is true, then what can you say about the individual propositions alpha and beta? You can see that if alpha implies beta is true, that implies that the second row won't occur. Only first, third, and fourth row occurs. So beta is true occurs with twice that of frequency for alpha is true. So we have the first, we can say that probability that beta is true is greater than probability that alpha is true, because beta can be true even when alpha is not true, when given the fact that alpha implies beta is true. This is an example of inductive reasoning. And we also have the deductive reasoning, that is the last row of the conditional truth table, that if beta is false, then alpha is false, and that is given as negation of beta implies negation of alpha. This is the example of deductive reasoning. So these are the two types of proof techniques that we use to reason about something from the premise, such as alpha implies beta is true. And what about how would such proof inductive reasoning or deductive reasoning comes into play when we consider quantum theory? So first is that the proof of reasoning for non-locality, where the Bell type arguments are basically inductive arguments, and GHZ and Hardy type arguments are the deductive arguments. And both the arguments can be understood in terms of a contextual hierarchy, which gives um, which gives us a strength of this Bell less than Hardy less than GHZ. This is some kind of contextual strength, and that is first proposed by Abramsky and Brandenburger in the shift theoretic formulation of the non-locality and contextuality. And similarly, we have this motivates us to see that what happens when we have the when you consider proof of reasoning for observer independent facts. We have the initial that Bruckner moment thought experiment, which is essentially uses Bell type arguments, that is inductive arguments, and the Frausch-Gehr-Renner thought experiment, which uses deductive arguments. We also have a ZZ argument, but for the observer independent facts, but for now we'll ignore that. Now this is what motivates us. Okay, so if this Bruckner thought experiment is essentially equivalent to the Bell type, essentially uses Bell type construction, and Frausch-Gehr-Renner thought experiments essentially uses Hardy type constructions. So is there a possible connection through contextual hierarchy? So this is the question, this is the broader question that I would like to convey. But before that, I will construct a contextual, what does the lesson for contextuality for only Frausch-Gehr-Renner thought experiment. So let us first discuss the Frausch-Gehr-Renner thought experiment, which is just which discusses the agents. So this is mainly the definition of agents are precisely defined in the work by Fuchs et al., where they have separated the role of agent to the inferences they make. So this is what this is mean by that agents are entities that can take action freely on the parts of the world external to themselves. So whatever propositional results they make, that is on that they make on the external world, not on themselves. And then we also have the facts. So according to Bruckner, the facts are the immediate experience of observer. If we take immediate experience of the observer, if we take observer to be an agent which takes actions freely on the parts of the world, then the facts are always experiences about the external world. So which can be precisely defined as that experimentally relevant unary I said unary proposition, but you can probably discuss binary propositions also. So facts are experimentally relevant unary proposition whose truth value is inferred by the agent through the experimental procedure. And then we also have the observer independence of the fact, for which is just for two agents A and B. If one agent is certain about another agent's proposition experimental result, then that agent is certain about that particular experimental result, which was obtained by another agent. That is observer independence of fact. And of course we also have the reasoning process that takes only unitarity of the quantum theory. But for here, if we want to go beyond quantum theory, you have to assume that this is an type of reversible computation. So an agent can model another agent's reasoning process through reversible computation. Now let's just discuss how the Faustiger-Renner experiment goes through. So we have two BCs. So we have two measurements, this fail and okay. And then we have the propositions, corresponding propositions, which is that the which says that experimental results corresponding to sigma z and experimental result corresponding to this fail and okay basis. So using these two propositions, we can just briefly state what how the FR experiment goes through. It starts with an initial state, and then at time t1, the first friend, he measures in sigma z basis. That is, he tests the truth value of the proposition z1, and then prepares another state, which he prepares another state, that is, if the experimental result is 0, the state is prepared in 0 state. If the experimental result is 1, the state is prepared is 1 by root 2 x, and the plus eigenvalue of the sigma x observable. And then again the second friend f2, he again tests the truth value of the proposition z2. And after that, both the Wigners w1 and w2, they measures in this okay and fail basis. And I have not taken into account of the fact that the Wigner 1 and Wigner 2, they measures in different time. The Wigner 1 measures in time t3 and Wigner 2 measures in time t4. For now, because we are only considering how they model about the respective friends' propositional results, how they infer, what they can infer about experimental results of the friends. So individual, when they measures, is for now is not important. It will be important if we consider the different versions, specifically if we consider a particular type of Faustiger-Renner experiment, which it takes, where we have uses two time probabilities. So from this is evident that now from this state they will apply the unitary reversible computation reversible computational reasoning process to get back psi t2, which is the measurmental state before uh, the mm, friend 2 or friend 1 makes any experiment. So in this sense, these are the so they will only infer about the unperformed experimental results, because this phi t2 is the state before the observation but after the measurement process starts, and they only make the observation when they only in the inference process they only apply when the both of them found this w equal to okay. This means when the proposition w1 and w2 is true. So they don't consider the propositional results corresponding to negation of w1 or negation of w2 or negation of w1 and w2, the other three or other three results. So what are the identities what can they infer? So you can see that if your w from the structure of it, you can see that uh, for two friends, if if you if z2 is true, that means the experimental result of the sigma z measurement for second friend is up, then the experimental result of the uh, first friend is also up. If that is, if z2 is true, then z1 is true, that is z2 implies z1. Similarly, we have, you can also see that if w1 is true, that is the first Wigner measures in obtains 1 by root 2. This will be 1 by root 2, okay, and fail. So 1 by, if they obtain a measurement result 1 by root 2 0 0 minus 1 1, then z1 is true, because the only contribution you have is from the last term of psi t2. And so we have, if w1 is true, then z1 is true, that is w1 implies z1. Similarly we can model other Wigner's inferring process, that is if w2 is true, then z2 is false. That is also can be seen from here, because w2 is true means that the it will only contribute from the first term of psi t2, and the first term of the psi t2 implies that the friend 2 will get negation of z2 to be false, that is the negation of the z2. Similarly we have the you can see that this w1 and the first three proposition, the second and third propositional inferences are about the measurmental results of their corresponding frame, that is w1 takes the system and takes the state corresponding to first friend's lab and then infer about his measurmental result. Similarly w2 infers about the second Wigner infers about the second measurmental result. But we have another sets of logical inferences, which is if w1 implies z2. That is also evident from here, because if w1 is true, is only correspond to the third term of the psi t2, and we have z, in that case only z2 is true, because second, for the third term, corresponding to the third term, the second Wigner will infer that the first Wigner will infer that the second friend will get z2 to be true, that is this. Is w1 is true, then z2 is true, and similarly if w2 is true, this z1 is false. So these are the five propositional inferences that one can draw from the Frauchiger-Renner experiment, but we don't, to get that argument, we don't need all of them. So to see that I have, this is the result correspond, this is the propositional inference, though informal propositional inferences taken from the Bruckner paper for the no-go theorem on the observer independent fact. You can see that this S1 corresponds to this W2 implies negation of Z1. Uh, we cannot directly see that, but that can be seen if we uh, go to this deductive reasoning argument. If alpha implies beta is true, then negation of beta implies negation of alpha. That would mean that if your Z1 is, sorry, if Z1 is true, then negation of W2 is true, that is W2 is false. Similarly, if S2 corresponds to the first propositional result, Z2 implies Z1, and we have the S3 that corresponds to the S3 or corresponds to this, the fourth propositional result, W1 implies Z2, and S4 is of course this both that post selection onto W1 and W2. So where in the Bruckner paper they have constructed the logical inferences by combining the results of the two Wegeners, but once we identify this S1, S2, S3 as the first, fourth, and fifth propositions, you can easily see that these three propositions are inconsistent with each other. Because if W1 and W2 both are true, it means Z2 is true and Z1 is false. But that is inconsistent with the fact that Z2, if Z2 then Z1. That can be easily seen from this truth table, but you can also see that, you can also argue that if sorry about that. So yeah, you can also argue that it is Z2 implies Z1 is that it is impossible that when Z2 is true, then Z1 is false. So so fourth and fifth propositions gives that W1 and W2 is true for Z2. If W1 and W2 is true, then Z2 and negation of Z1 is true, but which is
I'm
inconsistent.
sorry, Som, but you have 5 more minutes.
So I have to hurry it up. So you can see that there is inconsistency of the argument. So this inconsistency says that this is the inconsistency that uh, talks about this is the inconsistency that understood that put forward by the Frauchiger-Renner experiment. In the paper by Baumann and Veronica Baumann, Santo, and Bruckner, they have shown that this inconsistency disappears if we consider two-time probabilities. So these two-time probabilities, but this two-time probability says that we have a non-zero probability of this W1 and W2 implies Z1 and negation of Z2. This is not valid in the two, if we define the conditional probability as a two-time probability rule. So then we have the then what contextual relations, will come to that. The contextual relations is basically is that the contextuality is defined as the global inconsistency and the presence of global inconsistency of this type of joining of local propositions or local inferential propositions, And you can for the hard disk and also this is very easily shown that you can have propositional results that are inferred to be false, but nevertheless experimentally we can found them to be true. And so that is what propositional inferences. So you can see that as I argued before, that this sets of propositions, this W1 implies Z2 and W2 implies negation of Z1, and Z2, that first, fourth and fifth propositions, these three are internally inconsistent with each other. You can also see that the second, third and fourth, fifth propositions, they are also inconsistent with each other. It is easily can be seen because you consider the second proposition and the fifth proposition. You can see that it gives W1 and W2 gives you Z1 and negation of Z1. It gives both, which implies that both Z1 is true and the negation of Z1 is true, which is impossible. And similarly for if we combine the third and fourth propositions, it gives both Z2 is true and negation of Z2 is true. So you have the inconsistency is there also. And this is when we combine local propositions and get inconsistent results, that is what is a demonstration of contextuality. So this is what I have shown it here, that these pairs individually they are consistent, but when you combine them together, we get an inconsistent result. And similarly the standard Bruckner the standard Frauschgier-Renner experiment says that if the pair itself is consistent, but if we combine it with the proposition Z2 implies Z1, then we also have an inconsistency. So yeah, combining both of them, we can see that. So we have this triple and the tuple, they are individually consistent, but if we combine both of them, then there is an inconsistency, which is the demonstration of the contextuality is quantum theory.
Thank you, Som, for the talk. I can't see any question in the chat box at least. So, if anyone, okay, there is one. So the question is from Sumit Mukherjee. He asks, but for the said proposition, one can easily argue that some measurements are unperformed in the experiment. The reason it's that to validate all the proposition jointly, one has to make measurement in two such bases which are mutually incompatible.
Yes, so about that, you can of course argue that because they infer about unperformed experimental results, so there is an inconsistency. So you can always say that, and that is what. But still, I'll point out that there is you can argue consistency about unperformed result if we consider only locally consistent propositions. So it's only when we combine the results of the local propositions we get an inconsistency.
Okay. So next question is from Gautam Sharma. He asked, Weisman et al. Recently in a paper said that Bruckner's description of extended Wigner's friend scenario is equivalent to contextuality proof. Is there a hierarchy between Bruckner's consideration and FR experiment?
Yeah, I can read that. Yeah, that is what the goal of this talk is, to think about the to motivate the hierarchy, or how would you argue the hierarchy. The way the hierarchy in the Bell scenario, in the standard non-locality proof, the hierarchy is proved as follows in the Abramsky Brandenburger, or for the there is another paper by Hardy and Abramsky where they have constructed a type of logical Bell inequality from the uh, premises, from the propositional premises, that from the type of propositional premises that I have discussed in the first slide, and from there they have constructed an inequality, and it has been shown that that inequality is violated. and the amount of violation of that inequality is, for Bell it is lowest, for Hardy it is greater than Bell, and for GHZ it is greater than Hardy. So in this way the hierarchy is proposed. So I would hope that there is a hierarchy between some kind of propositional arguments, just starting from the propositional premises and construction of an inequality, which shows there is a hierarchy between the Bruckner's consideration and Nefer experiment.
Uh, I think no one has posted any more question. If anyone, okay. Sumit again asks that scenario works only when the propositions has global existence. If it is not so, then we cannot say anything about quantum mechanics and about nature, right?
Well, I don't know. If there is a good comment that was given, that was said by Fuchs in that paper that I have mentioned earlier. It said that quantum mechanics says something about the experiment in only case by case basis. What is measured and what what is measured and what about that. So yeah, that I'm not so sure that how that particular mm, how that particular statement would work here. What does it mean by case basis? So that is what that Fuchs paper that I have cited earlier, they have mentioned that quantum theory only works in case by case basis.
Okay, so next question is from Shiladitya Mal. He asks
Yeah,
that how hierarchy reflects in experiment.
that I'm not so sure how hierarchy. There are some experiments. I remember there are some experiments using uh, inter uh, intra-particle entanglement about hierarchy, but it's published in scientific reports. But I'm not so sure how that hierarchy will reflect in an experiment.
I think Gautam further extends his question and he asks that thank you. FR experiment has been criticized for inconsistent application of the collapse rule. Could it have any implication on the contextuality proof?
I'm not so sure about this. As I mentioned, this work is still unfinished, so there are lots of uh, things mm, that can be asked about this proof, this work, and specifically about this contextuality proof. And I think that in future we can think about something. What would be the implication for the contextuality proof in the inconsistent application of the collapse rule? Thank you.
Thank you so much. I think we are running out of time. So thank you so much for the talk.
Thank you.
So now I would like to invite the next speaker. So next talk is by Pratik Adhikari. He's from IIT Kanpur. And the title of the Pratik, can you share your screen?
Yeah. So
So
is
the
my
title of the talk is Observation of Quantum Synchronization and Blockade in Spin 1 System.
so am I visible and audible? Hello.
Yeah.
Okay.
Yeah, you can start.
Okay. So good morning, everyone. I'm Pratik Adhikari. One second. Yeah. So I'm Pratik Adhikari from IIT Kanpur. And first of all, I would like to thank the organizer committee so giving me platform to present our work. So here I will start. So in spontaneous synchronization is often observed in nature in various natural phenomena, like in dark forest when the fireflies start flickering. Initially, that they blink in a random fashion, but one can see that after some time, the whole forest turning on and off together. Um, in a large gathering, when people start clapping after some talk or some concert, So initially the rhythm of the clapping is random, but after some time the rhythm of the clapping gets synchronized. And also in when the two pedestrians walk side by side, their brain acts such a way that their footstep gets synchronized. So this all the example of spontaneous synchronization in nature. In 1665, Huygens first observed synchronization as a physical phenomena, and he observed that when two pendulums hang from a single substrate, and if they start oscillate with different frequency, and after some time, due to this weak coupling between them, and they oscillate in single frequency, in out of phase or in phase, depending on the initial state. So still then, there are several studies is going on in synchronization in classical domain mainly, but there is no signature of synchronization in quantum domain. So the basic criteria of synchronization uh, of a classical self-sustained oscillator with an external field or external oscillator is to have a stable limit cycle. A stable limit cycle is a closed loop in phase space such that any amplitude perturbation will not affect the cycle, but any phase perturbation will remain forever with the cycle. So in another word, there is basic difference between force-driven oscillator and limit cycle oscillator. So both the force-driven oscillator and limit cycle oscillator look same in the oscillation, the sinusoidal oscillation time domain. But at any instance of time, if there is any external perturbation on this oscillator, in case of force-driven oscillator, both the amplitude of the perturbation and the phase information will decay down after some time, and eventually the force-driven oscillator will start oscillate with its initial state. But in case of limit cycle oscillator, although the amplitude of perturbation will decay down, but the phase information imprinted on the cycle, and the oscillator start oscillate with this new phase, which is the phase of the driven force. So these are the basic difference between force-driven oscillator and limit cycle oscillator. Recently, Alexander Rule and Christoph Bruder shows that for a quantum system, spin half system cannot be synchronized due to lack of a limit cycle. So the next higher spin state, that is spin 1 system, has a valid limit cycle, hence can be synchronized. So here, this is the outline of my talk as well as our experiment. So we first create the spin 1 system in rubidium atom, which is cooled down in magneto-optic trapping, and we create the initial spin 1 system, and we stabilize this spin 1 system by putting all the atom from the edge state to the middle state. So we engineer to decay beam for this work, and this decay beam basically just put the atom from the edge state to middle state, and it will prevent any atom go from this middle state to back to the edge state. So this way we will stabilize the system in the middle state, and if we see the density matrix of this system in phase space, we will see that there is the limit cycle, equatorial limit cycle in this case. So this is the quantum limit cycle, and after that we incorporate to coherent coupling between this spin state, and this coherent coupling basically the external drive field which we apply from the outside, and we'll observe that the system synchronized to the phase difference of this coherent coupling. This is our primary observation. Okay, so this is our experimental setup of laser cooling of rubidium 87 atom. You can see there is that in the middle there is glass cell which is kept in a vacuum, and the laser beam coming from 3 directions eventually cool down the atom and trapped in a MOT, in a magneto-optical trapping, and we use this cloud of atom as our system. And this is the picture of the cloud of the atom, rubidium 87 atom in webcam. And this is the cartoon of our experimental setup, there are sets of beams, which I will be explaining gradually. At the center, there is Rubidium 87 atomic cloud trapped in a cigar-shaped moth. This is a real-time picture of that. And we initialize our experiment by putting all the atom in F is equal to 1 state. So this F is equal to 1 state of atomic state is basically used as a spin 1 system. So if you write down the density matrix for this system, we'll see that their density matrix only have the diagonal element. As a next step, we stabilize this system by creating two incoherent decay beam, which basically put the atom from the edge state to the middle state. And as I was saying, this decay beam basically prevent the atom from escaping from the middle state to any of the edge state, and the corresponding density matrix will have now only the middle state, the middle diagonal element. So the projection of the density matrix in phase space is a limit cycle where theta phi are the parameter of spin coherent state, and we have plotted here the Husimi-Q distribution as a function of theta and phi. Husimi-Q distribution is basically a function. Husimi-Q function is a projection of density matrix in spin coherent state basis. So one can define a synchronization function S phi, which captures the localization of Husimi-Q distribution along phi axis. So for limit cycle, as you can see that there is no localization along phi axis, so S phi is 0. So S phi is 0 indicates there is no signature of synchronization. This is basically limit cycle step. Now we incorporate two coherent coupling between this spin state, this T1, T10 and T0 minus 1, and also it called as this signal, tone signal. And due to this coherent coupling, the off-diagonal term of the density matrix now come into play. And if we project this density matrix in the this phase space, that is, if we calculate the Husimi-Q distribution and plot it in theta phi, we'll see now that Husimi-Q distribution have now localization along phi axis. So the localization angle depend on the phase difference between these two tone signals. And as there is localization of Husimi-Q distribution along phi axis, so the synchronization function is non-zero in this case, and this is the signature of synchronization. So to explain the signature of this coherent coupling, I will explain now a physical phenomena called electromagnetically induced transparency. For that, consider a three-level system where 1 and 2 are the ground state and 3 is the excited state. Now, and omega P and omega C are the coupling term between the ground state and excited state. And the corresponding Hamiltonian is look like this in rotating wave approximation. And if we rearrange the terms of Hamiltonian, we'll see that there is a coupling term, effective coupling term between the excited state and the superposition of the ground state. So this is called bright state. And this bright state actually coupled with the excited state. This is the coupling parameter. Now there is another state which is decoupled from the excited state, and this is orthogonal to the bright state. And this is called dark state. And this is decoupled from the excited state. If atom trapped in the dark state, the probe field will not observe the atom, and we will see the transparency in the probe field. So in the experiment, if we send some light to the atomic medium, this probe field, that sending a probe field to the atomic medium and scanning the frequency of the probe field. So we expect to observe a Lorentzian shape in the absorption profile in the detector, in absence of any other broadening in the system. So now, if we simultaneously turn on the control field and create the superposition between these two ground states, we'll see that there is a transparency window in place of absorption, where we expect that high absorption is there, but in the place of absorption, we observe the transparency low. Hello.
Yeah.
Okay. I thought I dropped out. Okay.
No,
So,
no.
so in the place of the transparency window, we'll now in the place of absorption, we'll now see the transparency window, and this transparency window basically signature of creating quantum superposition in experiment. So by creating this, we can see that okay, we now create the quantum superposition successfully. So in the time domain, if you see the probe pulse, this is the probe pulse in detector we can observe. And if there is no atom, there will be no absorption. But if we put some atom in the ground state of the probe field, and we see the some absorption. And if we turn on the control field simultaneously and create the ground state superposition, and the ground state superposition, creating ground state superposition means basically creating off-diagonal term of the density matrix. This is also referred as coherence of the system. This is nothing to do with optical coherence. And as a signature of this creating quantum superposition, we basically observe a transparency. So in the place of absorption, we'll see now that the pulse is basically transparent. Another way to explain this scenario is basically the system created a superposition state of atomic state and photonic state. So this is a superposition state of photonic state and atomic part, and this is called polariton. It's not atomic and not photonic state, but polariton, a mixed state of both atomic and photonic state. So the system basically creates this polariton, and if we turn off the control field little bit earlier, and then the part of the probe field will now absorb in the medium in terms of ground state coherence, and this coherence will eventually decays down after some time due to decoherence effect present in our system. But before that, before it completely decays down, if we turn on the control field, we can convert back the store coherence into optical signal. So this retrieve pulse, we call it retrieve pulse, will have now effect of this coherence, and it will have now information of the system in between this time, the storage time. So we use this retrieve pulse to observe the synchronization for our system. So now go back to our system. So for our system, there is 3 ground state, that is spin 1 system, 1, -1, 1, 0, and 1, 1 state. And we create the coherent coupling between this spin state, that is this tone signal, by using a intermediate excited state. So the probe field, pi polarized probe field and right circularly polarized control field create the coherent coupling between 1, -1 and 1, 0 state, and the probe and left circularly polarized control field create the coherent coupling between 1, 0 and 1, 1 state. So due to the effect of this coherent coupling, two ground state coherence, rho 1, 2 and rho 2, 3 also create in the system along with two dark state polariton, psi 1 and psi 2. So in the presence of probe field, now if we turn off both the control field, that is omega c s and omega c s minus and plus, if we turn off both the control field, we can store the generated coherence rho 1, 2 and rho 2, 3 in the atomic medium. And after some time, if we again turn back the retrieve control beam, that is this control omega c r plus and omega c r minus, this different control beam, if we turn on this control field, we can retrieve back the store coherence into optical signal. So now in the optical signal, we'll have the interference between these two store polariton or store coherence term, where phi c is the phase difference between store and retrieve control beam. So this phi c resembles the phase difference between these two tone signal. Apart from this phase difference phi c, we also introduce a magnetic field along the quantization axis of our system. So due to this magnetic field, a dynamic phase between these two polariton also generates. This dynamic phase basically the time evolution of this spin state with magnetic field. So So in the retrieve intensity, we observe both the effect of dynamic phase as well as the control phase difference. So here we plot the retrieve intensity as a function of storage time for delta, that is the dynamic phase, and phi c, that tone phase, both 0. And we observe that the retrieve intensity decays down to 0 as we increase the storage time. This is because the decoherence effect present in our system. Now, in the case of non-zero value of dynamic phase, there is a oscillation along with the decoherence decay in our system. So this is because of the interference between two stored polariton. We use optical block equation to simulate this exact scenario numerically, and our numerical simulation matches with our experiment with good agreement. And from the simulation, we can extract the density matrix element at any unit of time and use it to plot Husimi-Q function and synchronization function. Here we plot the retrieve intensity as a function of phi c and dynamic phase for symmetric and asymmetric decay ratio. So here we will see that this decay ratio will come into play for the synchronization. So here for symmetric decay ratio, we observe nice interference fringes, where for asymmetric decay ratio, the visibility of the fringes goes down. Our numerical simulation also matches with our experiment. And to observe the effect of synchronization in this coherent coupling, we are concentrating on the point where two tones are in phase and two tones are out of phase. So when the two tones are in phase, we observe the corresponding Husimi-Q distribution have a localization along phi axis. And in the case of when the two tones are out of phase, there is no sign of synchronization and localization of the Husimi-Q distribution along phi axis. So we can see that when the two decay ratio is equal, we have a region where there is no sign of synchronization. Now, in case of asymmetric decay ratio, we concentrating in these 2 points, and we observe the for when the two tones are in phase and two tones are out of phase, for both the point, the distribution has some localization, and this is basically signature of synchronization. Here we we use the visibility of the interference fringes to calculate rho 1, 2, and rho 2, 3, and use it to plot the synchronization function in the whole region. And as we expect that here also we observe that there is non-zero value of synchronization function for tone 2 when the two tones are in phase, but there is no value of synchronization, that is S is equal to 0 when the two tones are out of phase. And but the scenario changes when for asymmetric decay ratio, we observe that non-zero value of synchronization function in all region. So this happens due to quantum. Hello.
Pratik, yeah, you have 5 more minutes.
Yeah, okay, I'll wrap it up. Yeah, so this will happen due to the quantum destructive interference. And here we observe the quantum destructive interference and the dynamics between quantum destructive interference and incoherent decay, where we are concentrating on the point where the two tones are out of phase, and the dynamic phase has some non-zero value. And here we plot the retrieve intensity with increasing the incoherent decay, and you observe that both the retrieve intensity and the synchronization function is 0 in this region, which is basically a blockade of synchronization synchronization due to quantum destructive interference between these two tone stored polariton. Now, as we increase the incoherent decay beam, for asymmetric decay ratio, one of the coherence decays down faster than the other. As a result, the blockade condition lifted, and we observe non-zero value of synchronization function, and as well as the non-zero value of retrieve intensity in this region. And but for the symmetric decay ratio, this blockade region continues. Okay, so here we plot the synchronization, this retrieve intensity as a function of tone coupling, and we observe that a nice interference fringes with dynamic phase, but this simulation also showing same result. this is for phi c is equal to pi. So we are not observing any synchronization in the synchronization plot. This is for when the two decays are equal. And we concentrating on the point A, B, C and plot the Husimi-Q distribution. And Husimi-Q distribution also we are not observing any localization. But the scenario changes in when the two decay ratio are unequal. We observe some unknown time-like of features in the experiment as well as in the simulation. So both the synchronization function and retrieve intensity is increasing with the stone coupling and is forming an unknown time-like of shape. And we are concentrating on D, E, and F point. We observe that the Husimi-Q distribution have some localization along the phi axis. The localization angle changes or precesses with the dynamic phase. So this is one of our primary observation. So to conclude, we have used the Rubidium 87 ground state manifold as a spin-on system to observe synchronization. We use the experimental technique of storage and retrieval light to observe synchronization. And from the retrieve intensity, we plot the synchronization function, which portray the any value of, which is a measure of synchronization function. And the corresponding state, when we plot in the phase space, we observe that there is a limit cycle in when there is no coherent coupling present in the system, but the Husimi-Q distribution get localized when there is coherent coupling present in the system, which is signature of synchronization. Thank you.
Yeah, thank you, Pratik, for the talk. There are a couple of questions. If you
Yeah.
can see the chat box, otherwise I can read it out.
Okay.
Okay, so first question is from Shubham Singh. He has that, isn't this same as a spontaneous symmetry breaking of QFT?
Actually, that I don't know because we have not think that way. This is basically synchronization is basically as I was explaining that basically if you take two oscillator and just two oscillator has different frequency and after some time they start oscillating same frequency. So that is basically that. We don't know actually that way we can explain it or not.
Okay, so next question is from Aditi Sandhe. She asked that very naive question. I missed what kind of noise effects your system have. I mean, when you do numerical simulation, what kind of noise have you taken into consideration?
Actually, the noise, we don't take any such kind of noise, but we only take decoherence effect, that is the octagonal term in the Hamiltonian. So we have not taken any noise such of that. But we observe that that incoherent decay had some effect in the synchronization that we observe.
So next question is from Kritika. She asked that, could you elaborate the role of 0-0 state?
Yeah, absolutely. So basically, if you see the 0-0 state, 0-0 state is not present in the case of the spin half state. So 0-0 state is basically a phase symmetric state. So if if you take this density matrix, that is, if you put all the atom in the 0-0 state, and you will do that if you take the density matrix and plot it in Husimi-Q distribution. So basically, it is you can say that this state does not have any phase information. So basically, that is the way you can see that if you put atom, it will have a limit cycle. So this is a quantum limit cycle, you can say, like classical limit cycle. So 0-0 state is basically that. It is phase symmetric state. Yeah.
I can't see any more question. Okay, I think Kritika asked one more question.
What is the question? She's asking same question.
She hasn't written it yet. She just wrote that one more question.
Okay. Yeah.
So Kritika can ask directly. I mean, Because
Yeah,
We can. I can hear actually.
yeah. I mean, she can
So
switch on
if I
mic.
can ask,
Yeah.
can you hear me?
yeah,
But very. Your sound, the voice is very low actually.
It's low, Kritika.
Am I audible now?
yes, better.
Hello? Okay.
Yeah, now it's fine.
So, sorry, I think I wasn't clear. This 0, 0 state, in theory, spin 1, it's the equatorial state that the system stabilizes to.
Right.
But
right.
in your experimental setup,
Mhm.
you have this 0, 0, which is decoupled from all your dynamics. So I was basically asking, how is that, like what role does 0, 0 in this your 1 minus 1, 1, 0, 1, 1 state play?
Actually, that like what you said, that exactly same kind of actually role it is playing in that experiment also, because the when it is decoupled from the any of the excited state, any of the 1 0 or 1 minus 1 or 1 1 state, this is basically a limit cycle state. That's what you are saying. But
Yeah.
any other way, I don't think it will actually. We have not think of any other way.
I see. So it is not
Yeah.
actively participating in the dynamics of your 3-level system, right?
It is
Or
actively participating. It is actively participating because this is what actually creating the limit cycle state. So it is you see that when there is no coupling present in this system, so this limit cycle state is basically has no phase information.
yeah.
But when there is coupling, that this limit cycle state actually synchronized with the coupling phase basically. So that way, everything happening in the 0, 0 state, but with coupling and without coupling, basically.
Okay, thank you.
Hello,
Yeah.
hello. I'm Arnav Sarkar. I want to say,
Yeah.
like, maybe you are referring that 1 0 as 0 0. I mean,
Oh yeah, right.
yeah, yeah, yeah.
Uh, uh, This one, exactly the 0, 0
Maybe,
state.
yeah, maybe her question is about 0 0, which is totally decoupled from the.
Decoupled from the system. Yeah, I was talking about 1 0 state. Yeah, right. Yeah, thanks for the. Yeah.
I think there is a question also in chat box from Sheila.
Yeah, I can read it. Maybe. Yes, Shilarito, thank you for asking. So basically, in classical synchronization, as I was explaining, the classical synchronization, there is a well-defined limit cycle in the phase space, but in quantum synchronization, there is nothing called limit cycle. And I mean, there is limit cycle, but the thing is that the notion of the limit cycle is different here. So in general, I don't. I mean, you cannot make a general picture for both quantum and classical synchronization because the system is different. So we have to think different for quantum system. Yeah.
Okay. I think there are no more questions. Thank you, Pratik, for the talk.
Yeah. Thank you.
So I'll invite the next speaker. So next talk is by Soradeep Sesmal from Bose Institute. And the title of the talk is Exploring Relationship Between Genuine Randomness and Known Locality Using Hardy and Cabolo-Liang Relations. Soradeep, okay. You can share your screen.
Saurabh, you are not audible.
Yes, hello.
Yeah.
Now it's okay.
You can start sharing your screen.
Yes, I'm trying to do so, but Is it visible now, the presentation? Hello?
Okay, yeah, we can see it.
Okay, good morning, everyone. I would first like to thank the organizer for giving me a chance to present my work here. Um, this what today I'm talking about the concept of genuine randomness and its connection with non-locality. Specifically, by non-locality, I mean bell-type non-locality. Visual scenes. And this work is our ongoing work, collaborated with Shayon, Ashtozda, Dipankar, and Ilbosimo. And now to begin with, we first have to understand what is randomness. Randomness can be defined as lack of pattern or unpredictability events. In this cartoon that I have taken from Bilbert.com, that creature is telling 9999, and but we don't know whether this sequence is random or not, because this is the problem with randomness. We cannot never be sure whether it is coming from a deterministic pattern or the sequence is totally random, because so that's the question the creature is asking. That's the problem with randomness. You can never be sure. But why we bother about certifying genuine randomness? Because it has vast applications in many information theoretic tasks such as quantum key distributions or quantum networking system, or other than the cryptographical applications, it has some immense applications in numerical simulations of physical or biological systems, or some selection of sample from a finite population for statistical purpose. So certifying genuine randomness is very much important thing to do in our nowadays life where technology is so important. So, so one can argue that randomness can be extracted from some physical phenomena like tossing a coin or rolling a dice or spinning a silhouette, but spinning a roulette. But the problem is whether this phenomena truly random or not. Because if we know the exact initial conditions or the force applied, and by applying the Newtonian dynamics, we can actually predict the outcomes of the tossing of a coin or rolling of a dice. But so if we extract random numbers from this type of phenomena, those numbers are not truly random. Even one adversary can simulate that phenomena and can guess all the sequence of random number. So this so classical process like tossing a coin or rolling a dice cannot be used for extracting random numbers. Now, thanks to quantum mechanics, there is an inherent randomness present in it because of the Bond rule. Because the outcomes of measurement performed on a quantum mechanical system are truly random, and this randomness persists even if we have the full knowledge of the preparation of the state of the system. Because this type of randomness actually arises in quantum mechanics due to its inherent indeterminism, not like classical mechanics where the randomness arises due to subjective ignorance about the system. So random number can be generated by performing measurements on quantum systems and Bond rule certifying that randomness, and the random number generator based on this perspective is called quantum random number generator. So it seems that our problem is solved. We have a genuine random source that can be certified by some postulate. But wait, there may be a problem. If QRNG deviates from its intended design because of uncontrollable imperfections or tampering by an adversary leading to unavoidable biases. Because it may happen that the device is the device I got from a store is actually adversary is supplying the device, then adversary may tamper the device and we cannot be sure whether the device is truly quantum or not. I mean, the question is how we can certify the random number coming out from that device in a device independent way. So this may be a practical problem. Also, there may be a fundamental problem like apart from the wave function specifying the prepared state of the system, the state actually depends on ontic variables described within standard key, not described which is not described in standard QM. So by using that ontic variables, we can possibly predict the outcomes with certainty. So we need another way to certifying the randomness coming from any device by treating the device as black box. So that is called device independent random number generation is important. Now, recent work by Cavalcanti et al. Have argued that the Bell CSSH inequality can be derived from two different perspectives. One is that if we take the local realism assumption in the hidden variable level, that is the hidden variable is local and have some technique value. I mean, the idea of hidden variable implies the realism. So from there we can derive Bell CSSH inequality. And also they have argued that if we consider the operational level, that means in a lab what we do, we prepare some states and measure something on that state and collect some statistics. And so from that statistics, if we consider two assumptions, predictability and no signaling, which I will elaborate in my next slide, then it is possible to derive Bell CSH inequality. So what I mean by predictability is that predictability states if the joint state of each pair of particles is prepared by an agreed upon reproducible preparation procedure, it is possible to predict with certainty the outcomes of all possible measurements performed on the joint state of the particle. Here an interesting point is that I have explicitly written the reproducible preparation procedure. That means in operational level, the main two primitives are the preparations and the measurement. So here I fixed the preparation procedure. And by no signaling, that is impossibility of transmitting information from one party to its space-like separated partner, implying that the probability of occurrence of any measurement outcome in one wing is independent of the choice of measurement setting in the other wing. Note that this no signaling condition is different than the locality condition at hidden variable level, because the locality condition we are dealing with the event by event description. That means at every run, the measurement performed by another observer is independent on the outcome obtained by another space-like observer. But the no signaling condition deals with in operational level, that the whole statistics is independent of the statistics obtained by another space-like separated observer. Now, from these two assumptions at operational level, I mean the observed statistical level, that from predictability and no signaling, one can derive the factorizability condition. That is the factorizability of the joint probability distribution. And we all know that from the factorizability of joint probability, we can derive not only Bell CSH inequality but other forms of non-locality argument from the factorizability condition. So Cavalcanti et al. Have shown that from predictability and no signaling, we can obtain Bell CSH inequality. Now in this work, we have considered the Hardy relations, which are first introduced for demonstrating Bell non-locality without invoking Bell type inequalities. And that Hardy relations are characterized by the simultaneous validity of the following four conditions. That means these four joint probability conditions, where if we take three particular joint probability to be zero, then the fourth one should be non-zero. And the most interesting thing is that in quantum mechanics, there exist some states, let's say there exist some pure non-maximally entangled states, which contradicts, which satisfy this inequality. So Hardy argued that in a local realism domain, if these three joint probabilities are zero, then the P Hardy should be zero. But in quantum mechanics, there exist states which satisfy these four conditions simultaneously. And now from factorizability, one thing we note that here I have used a notation kappa which is actually the preparation procedure. Here I am not bothered about the state I am preparing. I am interested. The preparation procedure is used for the collection of statistics after measurements on that system. So if we apply the factorizability condition on this 4 joint probability, we will obtain these 4 equations, and by simple algebraic calculations we can show that that this condition, that p had greater than 0, is inconsistent with the factorizability conditions derived from predictability and no signal. So the simultaneous validity of the conditions imposed by the Hardy on the 4 joint probabilities is inconsistent with the assumptions of predictability and no signal. We have also considered another form of Hardy relations, which is known as Cavalier relations, and which is slightly different than Hardy relations. If you see the equation 1, 2, and 3, for Hardy relations 2 and 3 are there, these 2 joint probabilities are there, and this joint probability is taken to be 0, and this one is taken to be greater than 0. But in Cavalier relations, it's more general than Hardy one, because here I have here they have considered 2 joint probabilities as 0 and 2 non-zero, and their difference should be greater than 0. And for any local realist theory, the equation 1 becomes 0. But there exist some states in quantum states which satisfy this relation, that is PCL greater than 0 and other 2's are 0. So these Cavalier relations can also be derived from the factorizability conditions coming from predictability and no signaling, the similar manner to the way the derivation used for Hardy relations, the argument used for Hardy relations. I'm skipping the details, and now the thing is that simultaneous validity of these Cavalier relations is inconsistent with the factorizability conditions derived from the assumptions of predictability and no signaling. So in sum, what we find, that is violation of Bell inequality implies violation of factorizability condition, that implies violation of predictability conjunction with no signaling, and equivalently validity of Hardy relations and Cavalier relations implies violation of predictability and no signaling. Now we can take no signaling to be a fundamental principle of nature. So that means violation of Bell inequality directly implies the violation of predictability, or the validity of Hardy or Cavalier relation implies violation of predictability. That means if the measurement statistics violating Bell inequality or it validates the Hardy or Cavalier relations, then we can be sure of one thing, that the measurement statistics are purely random. It purely random and also private, because it is not possible to have a predictable model. It's not possible to construct a predictable model to explain those statistics. So in this way, we can certify randomness, what we call genuine randomness, because of the fact that this randomness can be certified in a device independent way, or in fact in theory independent way. I mean, any type of measurement statistics which will violate, the fundamental is the violation of Bell inequality or the validation of Hardy or CL relations. Now, so what I have said already, that perfect predictability of physical phenomena must be impossible. Now we have seen that Bell CSSH violation or simultaneous validity of Hardy or Cavalier relations are necessary to certify genuine randomness. Then the question arises that whether larger amount of non-locality necessarily implies increased amount of certifiable genuine randomness, because we have seen that actually non-locality and genuine randomness are 2 concomitant feature of violation of Bell CSH inequality or validation of Hardy or Cavalier relations. So it's the natural questions to be asked, whether there exists any quantitative commensurability between non-locality or genuine randomness. because this question is important in the perspective of the cryptographic or statistical cryptographic applications or some statistical applications, and in order to answer that question, we have to first appropriately quantify the obtained certified genuine randomness. So for this, I will discuss the quantification in more intuitive way. That is, let's say we have a set of events and it is occurring with some probability p, and we can say that the set of the occurrence of set of events is more random if the maximum probable event, if the value of maximum probable event is towards the value of the equally probable value, and the set of occurrence of that event is deterministic if the maximum probable if the value of the maximum probable event is goes towards 1. I mean, let's say Pmax be the maximum probability of the occurrence of the most probable event. Then if Pmax tends to 1, then the set becomes deterministic, and if the Pmax tends to the probability equal to the probability of equally probable events, then we can say that set of event is maximally random. But in that way, Pmax plays a crucial role for quantifying the randomness. In information theoretic perspective, entropy characterizes, in general, any class of entropy characterizes the unpredictability, or one may say the chaos in a present in a probability distributions. For example, Shannon entropy characterizes a average unpredictability of a probability distribution, and minimum entropy is one type of any entropy which characterizes the probability of the most probable probability of the occurrence of most probable event. So that's why H mean is taken as a quantifier of randomness, which is I will denote the quantifier as capital R, which is actually H mean, the mean entropy. Usually it should noted as H suffix infinity, because the Renyi parameter, if tends to infinity, then we get mean entropy. So that is minus log 2 Pmax. The base 2 is used because our unit, we have considered the unit to be bits, and it's a convention used for everywhere. So that's why we quantify randomness in terms of bits by minus log 2 Pmax. Now, if we consider the quantum mechanics domain, that we have prepared a quantum state and some measurements and we perform some measurement, then we'll collect some statistics of joint probability, and then I define that we have prepared a quantum state rho, and the amount of randomness that ensuing from the measurement statistics as R of rho xi yj, because here xi is the measurement of one party, say Alice, and yj is the measurements of another party, say Bob, and rho is the state shared between them. So the amount of randomness should depend on those three parameters: the state and the measurement settings they have chosen. So that will be R will be minus log 2 max of PAB xy, and here it should be noted that the joint probability PAB xy condition on xi yj and rho is can be evaluated from the trace rule, and that maximum is taken and the maximum is taken over the all possible outcomes, and the joint probability is given by the bond rule, that is trace of the where m subscript a condition on xi and m subscript b condition on yj are the measurement operators of Alice and Bob. So the scheme is that Alice is doing, let's say Alice chose x1 and Bob.
Saradeep, you have 5 more minutes.
Okay. So, so if we so now if we optimize over all possible quantum states and all possible measurement settings, we can obtain two values of R. That is, one value is the minimum value and one value is the maximum value. And we named that if we consider all states independent of any dimension or measurement settings, we will obtain, and we minimize the quantity R, we will obtain DI guaranteed bound of randomness. And if we take if we do the maximization over this quantity, we will get a maximum achievable bound. So so the importance of DI guaranteed bound is particularly in the context of cryptography, where cryptography, because actually it corresponds to the maximum guessing probability of any adversary. That adversary, if any adversary want to guess the measurement statistics, the upper bound of that guessing probability should be correspond to the DI guaranteed bound of genuine randomness. And I formally here I formally define the RGI guaranteed bound. That is, we have taken that minimization over all states and measurement settings, and if I say precisely the operational meaning, that is, given an arbitrary state and any combination of pair of measurement settings, if the statistics of joint measurement outcome violate Bell inequality or satisfy Hardy-CL relations, it is guaranteed that at least RGI guaranteed bits amount of certified genuine randomness is ensured. Now, some existing results is that for the Bell-CSH inequality, Pironi et al. Have shown that the RDI guaranteed bound and the amount of non-locality, which is evidenced by the violation of Bell-CSH inequality, are monotonic, has a monotonic relationship. That is, if we increase the value of non-locality, the amount of randomness will be increased, and the maximum value of the DI guaranteed bound is 1.23 bits when Bell-CSH value is maximum. Now we ask this same question in the context of Hardy and CL relations, whether this monotonic relationship persists or not. And using the SDP method, we have the details will be that details is in our paper, which will be coming soon in archive. So by doing the by using the SDP technique, we have found that in case of Hardy and Cavalier relations also there is a monotonic increasing relationship between the DI guaranteed bound and the randomness. But in case of Hardy and CL relations, we have found slightly less value that than obtained for the Bell-CSH case. Now, coming into the maximum achievable bound, the question is, while the amount for a given amount of non-locality, while the amount of randomness is lower bounded by the RDI guaranteed, the question is what one can extract what is the maximum possible amount of certified randomness that one can ensure for that kind of relations. So the existing, so for the maximum achievable bound, we have considered the device dependent case where we have taken a specific state and the measurement to be projective and try to optimize over all qubit state and projective measurements to find out what we can achieve by using Hardy and Cavalier relations. And in this respect, the existing results are that Asin et al. Have shown that close to 2 bits of randomness is maximally possible, which is the theoretical bound in the 2-2-2 scenario, because there are 16 joint probabilities and each measurement settings can produce four joint probabilities. So the maximally random set will be the equally probable set, which has the Pmax should be then 1/4 and the maximum randomness should be 2 bits. So Asin et al. Have shown that for the Bell-CSH case, it is possible to certify maximum 2 bits of randomness. And now we are considering whether, but Asin et al. Have shown that it is only for maximally entangled state in the 2-2-2 scenario. So we asked the question if it is possible to have close to 2 bits other than maximally entangled state, because in experimentally or practical purpose, the realization of maximally entangled state is quite difficult to realize. So this question is now we are analyzing, and we are searching for some states, and we also want to extend this question by using not confined within the pure non-maximally entangled state, but but for any state with independent of any dimensions or measurements. So, in conclusion, randomness plays a fundamental role in various physical and biological phenomena. Dependable and efficient random number generators are crucial ingredients of quantum technological application. And also, one can pursue in another direction that there are more facets of relationship between randomness and non-locality can be explored in terms of different measures of non-locality, other than taking the value amount of non-locality as some violation of some inequality. And then this in turn may lead to insights enabling development of the resource theory of genuine randomness, along with the understanding more closely the interplay between non-locality and certified genuine randomness. So, thank you.
So there are few questions. Can you see the
Okay.
chat box?
Yes, yes.
Yeah. So do I need to read them out, or you can check it out?
Yes. So Swati have asked, does large amount of violation
Before
always lead to?
Swati, there is one question from Shiladitya Mal. He says nice random noise also from background. And then he says, is there any pattern or non-randomness in the appearance of prime number?
Maybe in general, is there anything like quantum and classical? Okay, nice random noise also from background. So I think my internet connection is not so good, so that's why.
Okay, so I can read them out then.
Okay, is there any pattern in the appearance of prime number? So that I don't know whether any pattern or not. That the question is how to certify. If there exists some pattern, then how can you certify? Or in mathematics, it is not possible to certify randomness because, as Van Neumann famously said, that it is a sin to certify randomness from arithmetic study. And the next question from Sathi is that does large amount of violation always lead to larger non-locality? That I have just told in my last slide that in actually in 222 scenario the Bell CSSH violation can be taken as a measure of non-locality, is a defined measure, but other than that we cannot say that whether large violation of any inequality implies the large amount of non-locality. So for that reason, we have to take some valid measure of non-locality. And then Nitika have commented, interesting talk question. Is it correct to expect to find higher certified genuine randomness in generalized probability theories that admit higher violation of non-local inequalities? Okay, so recently another work of Asin have shown that the quantum theory actually is not quantum theory is actually a maximal random theory. So maybe the generalized maybe any probabilistic theory other than quantum mechanics. I think it is not possible to have maximum randomness from that theory because quantum mechanics is the theory which provides the maximal randomness. So and also has asked that has anyone studied okay there is a paper by Asin at PRL. I don't have this right now. The title thing, the maximum quantum theory is the maximal random theory. The title. The next question is: are there other ways to quantify genuine randomness, such as using Kolmogorov complexity algorithmic information theory? Have anyone studied this too? Okay. The problem for quantifying genuine randomness by using Kolmogorov complexity or algorithmic information theory should be in the certifying process because what cannot certify the randomness in terms of Kolmogorov complexity or algorithmic information theory, because it always rely on the complexity of the devices or the resolving power of the devices basically. So in principle, one cannot certify in those way. So that's why I don't think quantification should be done by using Kolmogorov complexity or algorithmic information theory. Okay, GR means okay. Actually, by the term genuine, I mean that the randomness that can be actually certified by in a theory independent way or in a device independent way. Otherwise, how you can say that this randomness is genuine? I mean, you cannot be ever sure whether this randomness is genuine or not. Other than depending on any physical principle. So here our case, we have assumption of predictability and no signaling, and if the measurement statistics violate those conditions, then we can sure about that the measurement statistics is violating predictability condition. So okay.
So I think there are no more questions and we are out of time as well. So yeah, thank you so much for the talk. So now I'll give mic to the next chair.
Yeah, so thank you, Priya, for chairing this session.
Yeah, thank you.
Thank you all the speakers in this session. So we move to the next session, and the next chair is Utkarsh Mishra. So we are happy that Utkarsh will be chairing the next session. So he's from the University of Electronic Science and Technology of China, and also alumni of HRI and the QIC group. So Utkarsh.
Yeah, hi. Can you hear me, ma'am?
Yeah, so can you stop sharing, Shauradip? Hello, Shauradip?
Okay. I got it.
Okay, thanks. So, Utkarsh, your turn.
Yeah, hi. So in this session, we have two speakers, Sandeep Mishra and Saptarshi Roy. So I would like to request the first speaker to please share the screen and we can start the talk. So I think the rule is that we will have a 25 minutes talk and 5 minutes for question answers. So I will remind the speaker when 5 minutes are remaining. Yeah.
Yeah. Am I visible and audible?
Yes.
Okay. So good morning, everyone. First of all, I would like to thank the organizers for presenting me an opportunity to present my research work over here. So the title of my talk is Quantum Coherence and Decoherence in Multipath Interference Experiments. Now we all know that coherence is ubiquitous in quantum systems, and we know that the quantum coherence basically originates from the wave function description of quantum systems and cannot be described within the framework of classical mechanics. And a consequence of which is the existence of the non-classical states which have no classical analog. And nowadays, in the context of quantum information processing, quantum coherence is now widely accepted as an important resource with important applications in photosynthesis processes, biological processes, quantum meteorology, quantum thermodynamics, etc. Now, we all know that the coherence has been known to physicists for long, but only in 2014, Baumgras et al. Elevated the quantum coherence to the status of a resource and proposed some measures to quantify coherence in quantum systems. And he basically proposed two measures. One is L1 norm of coherence, which is captured as the sum of the absolute values of the off-diagonal elements of the density matrix of the system given by this, where rho is the density operator of the system, n is the dimensionality of the system, and ket i's are the basis sets. So if there are off-diagonal elements present in the density matrix, then we can say that that system has coherence in it. Another measure of coherence introduced by Baumgras was relative entropy of coherence present, which is defined as equation number 2, where S rho is the von Neumann entropy of the system and rho dag denotes the state obtained from rho by removing all the off-diagonal elements of rho. And since the paper of Baumgras, various measures of quantum coherence has been introduced, and all these measures have some different motivations into it. Now, let us study about the coherence in multipath interference experiments. As far as coherence is concerned, we all know that coherence is intrinsic to the quantum systems and lies at the heart of matter-wave interference. And as far as Richard Feynman is concerned, he has said that the only mystery of the quantum mechanics lies in the double slit experiment. So in slit experiment, what happens? There is a source which is emitting some photons and it is passing through two slits. And there is a screen on which we are getting some interference pattern. But as and when we try to measure through which slit the photon has passed, the interference pattern vanishes. So there is a duality between the wave nature of the quantum and the particle nature of the quantum. So here we will be talking about the not the double slit interference experiments, but talking about the multi-slit interference experiment. Now, in the past few decades, there has been a spectacular progress in matter wave interference experiments, and the advanced technology now allows interference experiments with cold atoms, large molecules, Bose-Einstein condensates. So the natural question is, can the quantum coherence be quantified and measured in a multipath interference experiment? Now, in 2014, Baumgras et al. Elevated the quantum coherence to the status of a resource. And just in 2015, Bera et al. Introduced a normalized version of L1 norm of coherence and proposed a generalized wave-particle duality relation between arbitrary multipath quantum interference, where wave nature is characterized by the normalized L1 norm of coherence. So he basically proposed that the normalized L1 norm of coherence can be used to quantify the wave nature of the quantum in the multi-slit interference experiments. Now, this is the schematic of the multi-slit interference experiment. So there are 10 slits, and in all those slits, we have some detector states. So what happens? The state of the quantum after coming out of the slit gets entangled with the detector states. So the joint state of the detector and the quantum coming out of the slits can be written as the entangled state of the states of the quantum coming out from the slit and the detector states. Now, an entangled state of quantum and detector, when it emerges out of the multi-slit interference, then what we will do, we will trace out the detector states, and then the intensity distribution of the interfering quantum can be written like equation number 4. So here DI's DJ and DK are the detector state. So we can clearly say if the detector states are orthogonal to each other, then the interference terms will vanish out. And if the detector states are identical with each other, then the interference terms will have their role to the fullest. Now, let us assume that the state psi k, which emerges from the kth slit, is a Gaussian wave packet localized at the location of kth slit with a width equal to the width of the slit. Then the combined wave function of the particle and the detector as it emerges from the n slit can be written like equation number 5, where epsilon is the width of the slit and L is the distance between the slits. Now, in 2017, Paul and Qureshi showed that the intensity distribution at the screen can be written like equation number 6, where lambda is the de Broglie wavelength of the quantum, L is the distance between the slits and the screen, and theta j's are the phases associated with each slit. So the next question is, can the L1 norm of quantum coherence in multipath interference experiment be experimentally measured? Now, Paul and Qureshi showed a protocol in which we need to have the detectors in at least we need to have a tunable detector, and the tunable detectors should need at least two tunable states. One is the state where all the detectors are identical with each other, and the other state of the detector is when all the states of the detector are basically orthogonal to each other. So we have a detector which is tunable to these two states, then we can basically experimentally measure the coherence present in the multipath interference experiment setup. So what we will do, we will measure the intensity at the primary maxima where n paths are indistinguishable, and then we will measure at the same location the intensity where n paths are fully distinguishable. So if we know the intensities on the screen when all the detector states are indistinguishable, and if we know the intensity on the screen, if all the detector states are distinguishable, then basically we can measure the L1 norm of coherence in the actual experimental setup. Now, what we did, we basically introduced the environment into it, because as far as what Paul and Qureshi have done, they had basically not taken the effect of the environment into the picture, because real experimental setups are such that they are not free from coherence. So we introduced an environment also into the picture. Now, it is well known that the interaction of quantum states with an environment having large number of degrees leads to decoherence or the washing of the coherence. So, an initial pure state of the quantum system, which is a coherent superposition, decoheres over time into a statistical mixture. And ultimately, the environment would completely wash out the coherence, thus leaving the system in a state represented by a diagonal density matrix. Now, the next question is, can we monitor the decoherence of a quantum system by measurement of the coherence? Now, we used a well-known model of environment, which is described as the reservoir of non-interacting quantum harmonic oscillator, each of which interacts with the particle. So this model was given by the greats Caldera and Leggett and Decker. So the Hamiltonian describing the particle interacting with such an environment can be written like equation number 8, where x and t are the position and momentum operators of the particle, m is its mass, xj and pj are the position and momentum operators, and mj is the mass of the jth harmonic oscillator of the frequency omega j comprising the environment, and gj's are the respective coupling strengths. So the solution of this Hamiltonian is governed by the master equation, where rho x prime t is the reduced density matrix of the quanton after tracing out the environmental degrees of freedom. Gamma is the Langevin friction coefficient, and d can be interpreted as the diffusion coefficient, and T is the temperature of the harmonic oscillator heat bath. So for our system, the density matrix corresponding to the initial state of the quanton after passing through the slits can be given by equation number 10. Now, the initial density matrix evolves with time, and its diagonal elements in the position rho x prime t, which corresponds to the position probability density of the particle hitting the screen in a weak interaction regime, can be shown to be given by this expression. So this expression is a bit cumbersome, so let us simplify this. So staying within the Fraunhofer limits, where the width of the slit epsilon is much small in comparison to the fringe width, the expression for rho x xt can be approximated as this. So here, basically, if the detector states are orthogonal, then basically what will happen? The interference terms will vanish out. And if the detector states are basically identical with each other, then we will have maximum interference. Now let us see what are the main features of this experiment, this expression. The first, we can see that the intensity distribution shows that the decoring n-slit interference pattern is built up from all possible two-slit interference terms. So all two-slit interference terms are coming up over here in this summation sign. Now the environmental coupling modifies the pairwise contributions, and this effect of decoherence is neatly condensed into the exponential factor e raised to in this, in which multiplies the cosine term, giving rise to the interference, and this exponential term cannot be pulled out of the summation as it depends on j and k. So this is the decoherence term, and this decoherence term is depending upon J and K. So this cannot be pulled out of this summation. Now it can be shown that irrespective of the number of slits, all n slit patterns which when affected by decoherence degrade over time to a two slit interference pattern which eventually washes away. So what will happen irrespective of the number of the slits, all due to the decoherence, it will degrade over time into a two slit interference pattern. Yeah, so you can see from here. So these parameters are taken from the famous experiment done by Arndt et al. With carbon buckyballs. So here what we have done, we have taken a four slit interference term pattern. So here when no decoherence has taken place, then at t is equal to 0, we are seeing the interference pattern. And as time has evolved, the multi-slit features are vanishing and it has become an effective two slit interference pattern. And again, as time is progressing, the decoherence is happening, and the decoherence has played its role to the fullest, we are seeing the a single Gaussian. So all the interference effects have basically vanished out. Now, the distance between two pairs of slits is given by J and K. So larger the difference between J and K, smaller is the magnitude of the exponential decay term, hence faster is the decay. And this is the characteristic feature of the decoherence, where the decoherence time is inversely proportional to the basically the distance size. So the decoherence effect has its strongest contributions coming from the interference from pairs of slits which are furthest apart from each other, and its weakest contributions are coming from the interference from neighboring pairs of slits which are next to each other. Now, let us use the procedure or the protocol used by Paul and Qureshi to calculate the coherence of the quantum present in this system. So we can see that the coherence of the system can be given by equation number 13. And in equation number 13, this equation quantitatively captures the coherence of the quantum in terms of real parameters of the environment and coupling. So in this way, we can basically related the real environmental parameters with the coherence. Now, as far as the two slit interference experiment is concerned, the decoherence time can be calculated in terms by equation number 15. So here, what we are doing, the coherence is measured experimentally by the protocol as given by Paul and Qureshi, where the detectors need to be in two tunable states. So if I measure the intensity when all detector states are identical, and if I measure the intensity on the screen, if all detectors are orthogonal to each other, then we can get the coherence. And in terms of the coherence, we can basically get the decoherence time. So we have basically got the decoherence times in terms of the experimentally measured coherence in multipath interference experiment. So for two slit interference experiment with which way detection, one can experimentally determine the decoherence time scales given by equation number 13. So where lambda is the de Broglie wavelength of the quantum, L is the distance between the slit and the screen, M is the mass of the quantum, H is the Planck's constant, and I are the intensities as given by the protocol of Paul and Qureshi. So we can basically experimentally determine the decoherence times. Now, so results till now is that the decoherence degrades the interference in an interesting manner, with multi-slit features disappearing first and the interference reducing to an effective two-slit interference pattern. And the analytical expressions for the coherence of the interfering particle is obtained in terms of the parameters of the environment and the particle environment coupling. And we showed that the decoherence can be quantified by measuring coherence. And then for the particular case of two-slit interference, we show that the decoherence time scales can be experimentally determined by measuring coherence, which in turn can be determined by measuring interference intensities in a particular way. Now, in 2001, an interesting paper was published by me and its in Physical Review Letters. So what they did in 2001, reported a four-path quantum interference experiment via multiple beam Ramsey interference. So in this experiment, what they were doing, via a selective scattering of photons from just one of the paths, they were causing decoherence. However, contrary to the expectations, they saw an increase in the contrast of the interference pattern, demonstrating that the path selective decoherence can not only lead to decrease, but under certain conditions, to an increase of the fringe contrast too. So this is a counterintuitive thing which was shown by me and Ritz in their paper of Physical Review Letters. So what they are doing, they are causing decoherence and getting the path information, but still they were able to carefully manipulate the experiment so that with decoherence they are able to see an increase of the fringe contrast too. So this is a rather counterintuitive thing. So this is the schematic of the experiment performed by me and Fitz. So what's the difference between the earlier schematic and this? So here the environment is affecting just one of the paths, not all of the paths. In earlier work, what we did, the environment was affecting all of the paths, but here the environment is just affecting one of the paths. So decoherence will have effect on just one of the paths only. So what we did, we analyzed the multi-slit interference setup with which way detectors for situations where there is a possibility for which way path detection for a particular path, either through detector or by means of path selective decoherence. And additionally, in tune with the experiment of me and Ritz, the selected path has an extra phase of I. Now incorporating the effect of model of the environment as same as before, the intensity distribution on the screen can be given by this. So here we can see how the intensity distribution has basically changed. So here the decoherence is basically acting on the just nth path only, and in other paths there is no decoherence. Now let us find the quantum coherence. Now the quantum coherence can be calculated as the average of pairwise visibilities, where the visibility is the standard visibility given by Imax minus Imin divided by Imax plus Imin. So what we did, we calculated the coherence in terms of the visibilities, and this is given by equation number 18. Now, the parameters again we have taken from the experiment by Arndt et al. For the buckyballs. So for fourth path interference, what we are seeing, the red one, no, yeah, the blue one. So blue one is basically representing the interference pattern found on the screen at t is equal to 0. That means when no decoherence has happened on the nth path. And with time, the red graph is basically showing the interference pattern on the screen with progressive decoherence on the nth path. So what we are seeing, that the intense fringe contrast is basically increasing as the decoherence is playing its role to the fullest. So as decoherence is increasing, the fringe contrast is increasing. So this is in tune with the experiment performed by me and Fritz, where they have seen an increase of fringe contrast with progressive decoherence. Now, this is the graph showing the variation of visibility in red and the variation of coherence in blue with respect to the scale time for 3-path interference experiment, for 4-path interference experiment, 5-path interference experiment, and 6-path interference experiment. So what we are seeing, in tune with the experiment of me and Witz, with progressive decoherence, the visibility is decreasing, but again it has started increasing for 3-slit. Similar for the case of 4-slit experiment. The visibility has first started decreasing and again it has started increasing. But In contrast to the visibility, what we are seeing is that in all those cases, the quantum coherence as measured as the average of the pairwise visibilities is always decreasing with progressive decoherence. With progressive decoherence. So what we are seeing is that our results suggest that the traditional fringe visibility, while capturing well the intuitive idea of complementarity in the two-path case, fails in multipath situations such as those seen in the experiment by Me and Wirtz. So we explained the enhancement of fringe visibility and showed that even in this situation where visibility could increase with increasing decoherence or increasing with path information, coherence always decreases and preserves its role as the quantifier of wave nature. So what we are saying is that the traditional visibility is unable to capture the wave nature in the multipath interference experiment, but the coherence, which is measured as the average of the pairwise visibilities, is the true measure of the wave nature of the quantum in multipath interference experiment. So our results affirm the fact that the amount of decoherence can only be estimated by a measure of residual coherence and cannot be inferred by changes in the fringe contrast. This normalized L1 norm of coherence can now be considered as a true and legitimate measure of wave aspect of quantum in multipath interference experiment. Further, this quantum coherence can be measured experimentally in n-path interference experiment by taking the average of the traditional visibility of all available pairs of two-path interference by blocking the rest of the n-2 paths. So this work has been published in two of the papers in 2019. So I'd like to thank Guru Gobind Indraprastha University for providing me the Indraprastha Research Fellowship. So if there are any questions.
Yeah, thank you for the nice talk. So we have time for some questions. There is a question by Aditi. Can similar result be obtained with other coherence measures?
Till date, what we have done, we have basically used this L1 norm of measure only. So what I have done is that this L1 norm of coherence, with this we can basically get the true wave aspect of quantum in the multi-slit interference pattern. So we are working on some other measures also, like relative entropy of coherence, to see whether they will also work or not. Because as far as things are concerned, we know that the measures of quantum coherence are not monotone of each other. So they will not be, since they are monotone of each other, so naturally they may work, they may not. So this is still an unfinished work on which I am working on it. But till date, what I can say that this normalized L1 norm of coherence will work, but not so sure for the other measures of quantum coherence that we have to basically see, since this quantum coherence measures are not monotone of each other.
So are there any more questions? Okay, so I have one question. So you have this theta k. So these are the parameters of the initial state.
Yeah, they are phases. Yeah.
So is there any dependence on them? Any result, or they can be taken any value independent of the result? So I mean, so like the CIs are your initial state, right?
Yeah.
So I mean, so these theta k values are fixed, or from an experiment, or taken arbitrarily, or
the thing is that the theta k's theta j's, they will basically vary randomly. So they are the phases associated with the each slit, and these phases will vary randomly. So what we will do, we will basically, as far as the interference visibility is concerned, we will try to maximize this. and then I max and I min. So basically depending on that. So what we are saying that we need to have detectors at two tunable states. So in which the detectors are identical and in which the detectors are totally orthogonal to each other. So at least if we need to have the detectors in these two states, then we can basically be able to measure the coherence in the actual experimental scenario.
Okay, so all the thetas are same, or
Yeah,
I mean, okay.
they can vary in the actual experiment. They will come randomly.
Okay, I see, I see.
Yeah.
So okay, so I have one more question. So what is the for two-slit experiment? I mean this we have this complementarity relation, right? Like
Yeah.
the distinguishability and visibility
Yeah.
square. I mean d square
Yeah.
plus b square. So what is the motivation to go to the coherence rather than calculating the visibility for n particle interference pattern and
Yeah.
distinguishability for?
Yeah, so the major problem with this, because as far as the two-slit interference experiments is concerned, we have the complete duality relation between the visibility and which way path information. As far as the multi-slit interference experiments are concerned, the visibility has been proven by different people that it is not a true indicator of the wave nature of the quantum. So this is the basic motivation, because how to quantify the wave nature of the quantum multi-slit interference experiment. So what we have basically, or Bera et al. Have basically said that as far as the quantum coherence, which is measured as the normalized version of L1 norm of coherence, it reduces to the visibility for the two-slit interference pattern, but for multi-slit interference pattern, this visibility is not a true indicator as seen by the experiment by me and Witz. So what they are doing, they are getting the path information, still they are able to see an increase in the visibility. So one inference one can get that since the visibility has increased, so how we can quantify the visibility for the multi-slit interference pattern. So the basic motivation is to look for the wave nature of the quantum in multi-slit interference pattern. Like Bera et al. Have showed that the L1 norm of coherence and the can basically work as the can basically get the wave nature of the quantum. So what we had done, we had basically progressed on that lines only, and we have been even able to explain the famous experiment done by me and Witz. And now we have basically proposed that this L1 norm of coherence can now be duly said to be a good indicator of the wave nature of the quantum, and how this L1 norm of coherence can be measured in interference experiments. It can be measured as the average of the traditional visibility of all available pairs of two-path interference pattern by blocking the n-2 path. So we will take the pairwise visibilities.
Yeah, thank you. With this, we thank the speaker, and we invite the other speaker of the session.
Thank you.
Thank you very much. Okay, so the next speaker is Saptarshi Roy.
Hello, am I audible?
Yes, we can hear you.
Okay. So you can see my screen, right?
Yes. Okay. Yeah, perfect. So, Saptarshi, you can start your talk. Thank you.
It's fine? Okay.
Yeah, it's fine. It's fine. Yeah.
Yes. Okay. Thank you, Utkashta. So, hello everybody. Hello everybody. So, firstly, I want to thank my co-organizers for making YouQ-2020 possible in this virtual mode. Second, thanks to my co-organizers for giving me an opportunity to present my work. So, in today's morning session only, Shorav Divda talked about genuine randomness. So, in my talk, I'll be discussing about genuine entanglement in continuous variable systems. So, in short, so the essence of our work is this. So at face value, if you're dealing with continuous variable systems, we have to deal with sort of infinite dimensional objects. So this is extremely difficult. And so basically what you have to do is to sort of make a transition, a conversion from the handling of this infinite dimensional objects to small and manageable ones, and try to extract out properties of uh, the initial the big system from this small one. So basically the transition from this big and difficult stuff to us to small and manageable objects is sort of the in essence what we are trying to achieve in our work. And so without further ado, this is how I plan to lay out my talk. First, an obligatory introduction of entanglement and genuine entanglement, then come to the core results of our work, where we talk about the computation of multimode entanglement for continuous variable systems, talk about Gaussian and non-Gaussian states, and then finally conclude with a SWOT analysis and some future prospects. So in this work, we're dealing only with pure states. So all the overviews and stuff will be only for pure states. So firstly, in the bipartite domain, things are very simple and just two options arise. In two parties, things can either be entangled or it is a product, pure states, of course. And you can easily measure this entanglement by computing the entanglement entropy of the by the von Neumann entropy of the reduced density matrices. So things are simple, quantification is simple in the case of bipartite entanglement. But once when one moves into the multipartite domain, and if you take the example of this three parties, okay, so there is a possibility that states can be non-genuinely entangled product or genuinely entangled. Okay. So you can see that from three-party onwards, there can be a possibility of non-genuine entanglement as well as genuine entanglement. So in this work, would be only dealing about the business of genuine entanglement. So this is what we'll deal with, the genuinely entangled states. But unlike the bipartite case, the problem here is that the quantification of multipartite entanglement, in particular in our case the genuine multipartite entanglement, is hard. We'll describe why it is hard later, but before that I want to motivate and advertise that it is a hard problem worth pursuing, because in the case this genuine multi-party entanglement turns out to be a useful ingredient in especially in quantum networks and stuff like that, where the presence of multi-party entanglement is essential to achieve these quantum information processing tasks. And not only from the theoretical frontier, people have been talking about verification and sort of calibration of this multipartite entanglement in experiments as well. So it's a well-studied thing from both sides of the spectrum. So the sort of the general strategies to quantify this genuine entanglement is can be divided into two parts. The first one is a computationally easy one, is sort of the monogamy based approach, where one attempts to construct a multipartite measure by taking, say, specific combinations of various bipartite quantum correlation measures. So we'll not talk about that, but instead talk about a more rigorous procedure, which is sort of the which originates from the geometry. So it's a distance-based measure. So so in the distance-based measure formalism, so what we try to achieve is how we define this genuine entanglement is the minimum distance. So suppose you have to compute this. Genuine entanglement of the state rho, and we take we define it to be the minimum distance of the state from the set of non-genuinely entangled multipartite states. And this optimization, this minimization is that makes the problem hard to do. Okay. But in the case of pure states, one can have a simplification. The simplification is typically basically due to the fact that for multipartite pure states, you can apply Schmidt decomposition, and using Schmidt decomposition. So one fact is that you know that a state is genuinely entangled, a multipartite state, if you take the Schmidt decomposition in any bipartition, the Schmidt rank will be greater than 1. Okay. So this is the criteria for a pure state to be genuinely entangled. And sort of you can use this mid decomposition to simplify the optimization problem, and you can sort of express the sort of the genuine multipartite entanglement content, which you call as the, and this measure is the GGM, generalized geometric measure, in terms of the Schmidt coefficients of the bipartitions. So what you do? You do first calculate the Schmidt coefficient of all possible bipartition by finding the eigenvalues of the reduced state, and find out the maximum eigenvalue from each bipartition. Okay, and what you do is subtract the maximum of the maximal eigenvalues obtained from each bipartition. So basically, this gives you the GGM content. So expressed in terms of the Schmidt number. So basically, this is the algebraic representation, but the origin is geometric. So all said and done, this is fine. And now what we want to do is that extend this concept of GGM for multi-mode systems, where you see that the dimension of each party is infinite. Okay. So this is the big versus small thing that I was talking about. So at face value, what you have to deal with is that to find out the eigenvalues of infinite dimensional matrices. So this is the big and difficult thing that you have to do. And now see how one can make it small and manageable. Now, in the case of genuine multimode sector of genuine multimode entanglement, firstly I talk about first a general intro, and then I'll discuss about Gaussian state, then non-Gaussian states, and let's see, and then enhancement via non-Gaussianity. So you see that when you specify sort of a continuous variable state in some sense, that it might be a state of a harmonic oscillator or a quantum optical state, you see that even in the case of a single mode, you have to specify infinite number of numbers, the big thing, the infinite number of numbers. So the question which I try to address, that whether we can do better, whether we can simplify, even if it's for a special class of states. And as you all know, it has been discussed earlier in this conference also, that for Gaussian states, there is a class of continuous variable states. You can do much better. For example, in the case of a single mode Gaussian state, you can get away with just specifying 6 numbers. The first moments are Q and P. The Q and P, you can think of the position and momentum of a harmonic oscillator, or the electric and magnetic fields of the quantum optical state. So you can just get away with specifying 6 numbers. The first 2 moments, if you want to think in that way, the Gaussian. So you see that one of the most famous example in the single mode sector is that of the coherent states, and you can just specify a coherent state very simply using this for the phase space formalism, by using the only thing you need is this alpha. Okay. And sort of just for information, that the most general single mode Gaussian, pure Gaussian states are squeezed coherent states, where you see that the vacuum is just identity in the covariance matrix, the second moments, and so as the coherent state. And in the case of squeezing, what you have is squashing in one direction and elongation in other direction, keeping the sort of the product of the variance of the uncertainty constant and saturated to the minimum one. And so you see that this coherent states are called the displaced vacuums, because you see that all the sort of the properties, essential properties, are same, except that it has been displaced from the origin to some point whose address is specified by the complex number alpha. And when we move on to multimode case, people and also us sort of neglect this displacements in phase space, because the entire correlations of a multimode state is sort of, we can think, is stored in how the quadratures are squeezed and elongated, squashed and elongated in various directions. So basically we'll forget about the displacements and only talk about the second moment covariance matrices. So these type of states were also discussed earlier in various talks, so just for your reference. So you see that the big versus difficult versus small and manageable thing, we have a sort of a ready-made prescription using the phase space formalism, where we can sort of reduce the number of numbers to specify the system. But now the question is, we have to compute the sort of GGN, the genuine entanglement. How from this small, this covariance phase space formalism, we can extract out the GGM content, which were dependent on the eigenvalues of a state which was this, which would have been described by an infinite dimensional matrix. So this is how I would describe. So generally, the first two moments I was talking about, and neglecting the first moment. The second moment for a multimode case is given by this simply, and this Ri and Rj sort of is a vector containing all the propositional momentums, or all the quadrature variables, all the electrics and magnetic fields of all the modes. This is a M mode state. Okay. Now you see that all you need to know about the state is contained in this covariance matrix capital lambda. And now I'll discuss about a theorem that we need, is that using we need in our proof, is that what we can do is that we can diagonalize, given any covariance matrix, we can sort of diagonalize by using symplectic transformation. Why symplectic? Because we are working in the phase space, and these symplectic transformation preserve the canonical commutation relation. So these are the go-to operations in the phase space. And how the diagonal thing look like? It's a doubly degenerate matrix, where you can represent it as the direct sum of this mu I times the identity. So you can think that these are the individual modes of the M mode system, and these nu i's are called the symplectic eigenvalues. Okay. And if you want to ask that what the state in the usual notation looks like, so the diagonal one, it is just a product of thermal states with the temperatures which can be expressed in terms of the symplectic eigenvalues. So you see that this is the first step of sort of making a connection between the symplectic eigenvalues and sort of the eigenvalues of this the original state, because you see that these eigenvalues are what we are actually after. So you see that this is the schematic that what we are trying to do. Big and difficult row, equivalent description capital lambda, small and manageable, and you can do a symplectic to the diagonalization to get a diagonal, and which is equivalent to a tensor product of thermal state. But you see that this entire process, in this entire process, the eigenvalues of rho and this product of thermal states are same, because it's just unitarily connected. So good. Now to finally pull together the proof, I just note down and recall that what we already know. We know what is the canonical expression of GGM is. It's 1 minus maximum of the maximal eigenvalues obtained from each bipartition. And the we know that if you have a tensor product of states, then the eigenvalue of this tensor product is the set of the product of eigenvalues of each of the states. And one thing, you see that maximal eigenvalue we need, and we know that the maximal value of the thermal state is basically its first eigenvalue, the n equal to 0 term. Okay. So it's very easy. And finally, the thing that I want to say, that given a sort of covariance matrix lambda, you do not need to go through the cumbersome procedure of picking out a symplectic operator which diagonalizes this capital lambda. You do not need to do that, but because you only need the symplectic eigenvalues nu, which we can easily do by using this formula, where you pick out the positive eigenvalues of root over minus 1 times the symplectic matrix times the capital lambda. So this is what you need to do to get out to pick out the symplectic eigenvalues. Now, so you see that we are almost there. that we know that how the maximal eigenvalue is related to this symplectic eigenvalue, because we know how this beta is related to the symplectic eigenvalues, what we did in the last slide. Okay, this is what we know. And now finally, to pull together everything, and sort of when you are working with a M mode reduction of a N mode state. Okay, so the bipartition that we are talking about is M modes and capital N minus M modes. Then what happens is we know that the eigenvalues would be the product of the eigenvalues. But again, we know that we can represent it as the product of thermal states. And as you are wanting the maximal eigenvalue, we put the n index to 0 for every mode, and hence we get the maximum eigenvalue as a product of these terms, which was the maximal eigenvalue in the case of the thermal states. And substituting the value of beta in terms of the symplectic eigenvalues, we recover this. So this is what we need basically, and this is how we prove our sort of the first theorem, that given a n mode state, you take all possible m mode reduction, all possible m mode reductions up to so non for the making it non-trivial, taking the non-trivial maximal eigenvalues up to this n by 2 is sufficient, and then permute and take all possible m mode reductions, and 1 minus the maximal of the maximal eigenvalues gives you the GGM content of this n mode state. So excellent. So the small matrix capital lambda, we can find out the symplectic eigenvalue, substitute in this equation, we get the GGM value, the genuine multimode entanglement of this n mode state. So we had I'll not describe the prescription, and we are very happy that there is a simple formula for it. And before we were the situation in the country is such that our talks might need to include one nationalism slide. So here is one, and our version of this, that you give us a covariance matrix, is all we wanted to now after the formula was set up, that we were just wanted some covariance matrices of pure Gaussian states, and we want to compute the GGM. And now let's start. Let's now take some examples, and first start with a very simple one of a 3-mode state. So we copied this state from this review from Ferrero and Paris and others. So you see that how simply we can do it. So first you need to consider all the bipartitions in the state, and you see that all the bipartitions are identical. And as a matter of fact, this taking out partial traces in this phase space language is very easy. You only pluck out the block of modes that you need, and this is the covariance matrix of reduced covariance matrix. So all the relevant reductions are single mode, and all are identical due to symmetry of the state. You find out the symplectic eigenvalue and hence compute the GGM. Very simply. And now another example, we go to 4 modes. This is from Tomognoda's paper published in 2016, and so this is the 4-mode state, and we want to compute the GGM as well to show you a slightly more difficult example. And this would be sort of a 8 cross 8 matrix, because it's 3 modes, and you see that the single mode reductions again are all identical. Half times cos hyperbolic are identity, and the non-trivial 2-mode reductions are this. These are the only things we need to consider, because we have 6 of these and 2 of these reductions, and when you pull it all together, these are the 3 non-trivial reductions that you need to consider. Find out the symplectic eigenvalues of each, construct the maximal eigenvalue using the formula I just told, and then you can plug into the formula of GGM and you get it as a function of the squeezing parameter R. And you see that there's no, we cannot guarantee that which one would be the maximal, and depending on the value of R, there can be transitions of, so the maximal of these 3 you have to choose depending on the value of R. Okay, all said and done. I'll not bore you with any more examples of Gaussian states that we can compute. All said and good. But this was everything till now was perfect. That there was no problem, and we could just extract out the GGM very easily. But the continuous variable states are the Gaussian states are only a part of continuous variable states, and everything and we cannot do everything with it also. So as an example of something we cannot do with Gaussian state is the classic example of distillation. You cannot distill Gaussian states with Gaussian operations. Okay? So, and there are many other examples that we cannot do if we restrict ourselves to Gaussian states and Gaussian operations. So basically, then we have to move into sort of the regime of non-Gaussianity, and we sort of check that we sort of expect that we can get an enhancement of the GGM value over the Gaussian value via degaussification. And there can be various ways by which we can degaussify states, and sort of I would choose one by using photon addition and subtraction. Why we choose that? Because among the other techniques of degaussification, this seem to be experimentally feasible, and it has been done quite a lot in the experimental sector, adding or subtracting photons to a Gaussian state. And why we expect enhancement? Because, well, there are a lot of results. I just highlight three where they show that that they can enhance bipartite bimodal quantum entanglement by photon addition and subtraction, non-genuine of course. And same thing was reported for a four-mode state by Kolmogorov and others from our group. And we also actually did sort of a study where there was an enhancement of Bail inequality violation by this photonic operations, and you also considered some noise. So basically, this is the motivation of expecting an enhancement in the case of this genuine entanglement also. And let's see what happens. Our example that I would show you is the case of the four-mode squeezed vacuum. I'll say this is a four-mode squeezed vacuum. There are other ways you can define it. This is sort of an easy one, and sort of I'll not bore you with this. And now the point is that in the case of Gaussian state, the transition of this transition from big and difficult to small and manageable thing was sort of uh, guaranteed by sort of the phase space formalism. But in this case, there is no such mathematical simplification that we can offer. So we opt for numerical techniques, and we do it by truncation and checking for convergences. Okay. Now, I'll just flash some results, and to just recap what you are doing, taking the four-mode squeeze vacuum state, adding or subtracting photons, and seeing and trying to see whether there is an enhancement in the GGM value over the Gaussian. And we are happy to report that yes, we can have found that there is an enhancement, and in the case of this single mode operations. This is for single mode operations, and we see that the sort of this sort of the subtraction is sort of better than addition, because this subtraction, you see, this is for photon subtraction, and this each circle represents the number of photons that we have subtracted, gives more entanglement, more enhancement of GGM compared to the addition process. And these are for two different squeezing parameters, are 0.4 and 0.8. And this feature also persists when you add photons or subtract photons in two modes. That this was for only for one mode, single mode photonic operations out of the four, and you can add or subtract in the two modes. Okay. And you see that if you subtract the GGM and the GGM value for photon subtracted state and the GGM value on photon added state, you always get a positive value in the entire plane. That is, in the entire two mode sector, as just in the single mode sector, subtraction gave better enhancement. Okay. I'll sort of skip. So there are these two slides which sort of deal with. So actually, what we did is took out all possible combinations of photon addition and subtraction, and sort of checked how they behave. Okay. So I just presented two simple cases. I'll skip these. And now the natural question that comes to our mind is that whether why subtraction is better than addition, or and whether it is a generic feature or not. ठीक है. We sort of try to address this question by calculating non-Gaussianity, because by photon and addition or subtraction, what we are actually doing is to introduce non-Gaussianity into the system. So let's measure that and check whether there is a correlation or not. But unfortunately, what we find that although we can sort of explain the enhancement qualitatively, that it is becoming non-Gaussian, so that there will be enhancement, but to pin down why subtraction is better than addition, in this case at least, is not that easy, because you see, for another non-Gaussianity in the case of this photon addition, at least for these two mode operations, is greater than the non-Gaussian for subtraction. But you see that the fractional enhancement in the case of photon addition is much smaller than the fractional enhancement in the case of photon subtraction. So this is
Saptarshi, you have
sort of
5 minutes left.
not a conclusive answer. Thank you. I'll wrap it up. So you see that this is not a conclusive answer, and I would go on to say that this feature has been analyzed in other studies as well, and no sort of, as far as we could study, we could not get any conclusive answer to that. And to make situations worse, that if the this is not ubiquitous, that subtraction is not always better than addition. So in one of the other example that we have studied, sort of this addition of photons gave it's a 3-mode state. Addition of photons gave better GGM than photon subtraction. And in the enhancement papers that I was quoting to you about this bimodal entanglement enhancement, in the 2-mode case, the addition was sort of better than subtraction. In the 4-mode case, the subtraction was better than the addition. So basically, there is no sort of one quantity answer that you calculate this. If it is more, it will give you more GGM. We cannot answer like that. But sort of this is up to which we understand the situation. And let's not dig deeper into that. And so there are other examples and other features that, of course, due to lack of time, I missed. And you can check it. Check this, explore this in this paper on which the talk was based, and it has been done in collaboration with Tomognoda and Aditi, and so that's that. So I'll end the formal talk here, and I'll now conclude with the SWOT analysis. So this I would say that this the strength of our work is that we could pull out a scalable computation of GGM for Gaussian states and some non-Gaussian states as well, as you saw. So I think that is a strong point of our paper. And the weakness, the first thing, of course, as all of you have also witnessed, that it's the limited for application, limited applicability for mixed state. So you could only do this in the pure state scenario. And the last thing that I discuss is that the addition and subtraction business, although we got enhancement, but the why question was sort of not satisfactorily answered. So we want to answer that, and we want to continue with working in this field by sort of by trying to manipulate these Gaussian states and even non-Gaussian ones, and see by measurement or stuff like that, and to get enhancement. And threats, well, there is only one threat. That's why we have to do it in a virtual mode. So hope the world gets well soon. And sneak peek in the future, what we plan to do in the future. So I just want to tell that what we actually done is that took the concept of this genuine multi-party entanglement and pushed it into a regime whether it is computationally difficult. In the multi-mode case, where you have finite number of systems, but the dimension of each system is infinite or very large. So we sort of address this. The next limit of computational difficulty is presented in the case where the dimension of each system is finite, but you have infinite number of them. A typical example is the spin chains, where we have sort of recently utilized this concept of genuine multipartite entanglement of a model that we actually discussed discussed a couple of years back. And sort of what we find that about this paper was about detecting dynamical quantum phase transitions. And so we found that these fluctuations in this genuine GGM is sufficient to detect is a sufficient condition to detect a DQPT. So basically, this computationally difficult regimes of this continuous variable systems or spin chains, this GGM is a very useful quantity. It can give us not only from a utility perspective that it is a resource, it fuels this many quantum information processing tasks, but also it can address some fundamental questions like whether a feature like DQPT will happen or not. So we are continuing our work in this direction with Ganesh, whose poster you saw last day, and Ganesh and Srijan, and you can watch out his poster, which will be presented on the next day. And with that, I conclude, and that's what I had to say. Thank you.
Yeah, thank you for the nice talk. So we have time for some questions and comments. So if anybody has question, please directly ask to the speaker. Okay, so can I? Okay, so let me start. So I have this question about this. So you said that this Gaussian state, they have a 6 parameter, right, or 6 expectation value that we have to calculate in order to get the state. So, but rho is like big state. So
Yes.
do all the other correlators reduce to those 6 one, or they don't appear at all? Yeah. So, for example, like in the
You can you can express all the higher moments in terms of these first 2 moments. Yes.
Okay.
Yeah, just in the case of these Gaussian functions, like that, you can express all the moments in terms of these first 2 moments. So we can do that. Yes.
I see. Yeah. So I think people should ask question because Satarshi put the slide on Subhash Chandra Bose. So I mean, it's like, to mujhe lecture though, I will ask questions. So yeah. Okay, so one more thing that I didn't probably I probably miss this GGM. Is it related to any other measure of entanglement, or it is like bounded by say Fisher information, which is also kind of multi-party entanglement measure? So is GGM is somehow bounded with other or related with other entanglement measures, or it is very independent? So if you have any comment on that.
Yes. So maybe I cannot comment I cannot do a very good comment, but as far as I could sort of in the domain of this multipartite entanglement so you can have you see there is a concept of this k separability where uh, so I'll just tell in this way that instead, so if you have n party state, so one possibility is that you can have all the parties entangled with each other, and then you can have the possibility that n minus 1 parties are entangled and is product with the other. So basically the entanglement comes in various forms. I think form is a bad word to use here, that entanglement sort of can be different in the sense that which was unlike the biparty, which is entangled or not. So I think this genuine entanglement is sort of unique in the sense that everything is connected with everything. Every party is entangled. So if you there is other geometry based measures like the geometric measure of entanglement, where sort of you consider all these type of states. So um, in some sense these are related, and in some sense these are not. And for example, I might quote one of my own our one own results, is that so if you generate randomly generate states, multipartite states, what you can see is that that with the increase in number of parties, almost all states become possesses maximal genuine entanglement. Okay. the random states. So I can feel that I have not done a good job in answering your question, but I think this is as far as I can answer.
That's good. So, is any experiment where this measure have been like accessed in any experiment done for
Yes.
DGM?
There are experiments. Yes. So you see that what I have quoted here is that there are, so what we dealt with was the exact computation of GGM. And there are other works where we know that in the case of entanglement, one party is witnessing it and other party is actually quantifying it. So basically there are I could find a lot of experiments where there have been quantification verifications and certifications of genuine entanglement in quantum networks. And you can think that it has been operationally quantified in the sense that you know that unless you have this genuine entanglement or multi-party entanglement, you cannot have a good performance in the quantum information processing you are doing in networks. In a very last comment was very loose, so it was not that rigorous.
Oh, okay. So, thank you of both the speakers of this session. So, I think we end this session with this, and I hand over the
Thank you.
mic
Thank you,
to the.
Utkarsh.
Yeah, thank you.
Thank you, Utkarsh, for chairing the session, and thanks to the speakers and chairpersons of all the chairpersons and speakers of the morning session today. I think we go out now and have lunch, and we meet again at 4:30. And there will be a few talks, and then a few poster session, and then there's the keynote talk.
Chandra, you can stop the live.